Good morning and happy baby Friday. I am Gabe, the O-Scope Wizard. Thank you for joining me in the Techno Lair on what is hopefully a very exciting show because we're going to nerd out for about 20 minutes or so, maybe 30 minutes. But today we're going to try to answer some questions about whether I should use analog filtering or digital signal processing as the filter for my subwoofer in a bucket. This is my bucket, and inside of this bucket is the subwoofer. And ultimately, I want to bury this in the ground outside beside my driveway to create a little bit of bottom end to my driveway sound system that I started with the DIY Sonos style amplifier. And now we're adding, hopefully, a wireless subwoofer to that system, which I'm pretty excited about. So let's get into it. We are going to hit start, and we are going to go pretty quickly into the different things. So what are we doing today? We are, I suppose I should probably put the title up. Let's show it, and then maybe this is a analog filter. Is that analog filter? I can never spell live. Analog filter versus digital filter fight. There we go. That's what we're doing today. I think that's what we're doing. Wait. There we go. I want to move here. Get me over here today. Analog filter versus digital filter fight. We're going to see which one is better. Because I'll tell you what, I have been struggling with my filter design. And you can see in the background is my analog filter. So we've been using a TL072P op amp from Texas Instruments. And it's a very popular op amp. And in fact, if we go over to my browser window or my monitor here, we can check out data sheet for it. And the reason I chose the TL072 is because there are two op amps and one tiny little 8-pin chip. So I can cascade active filters, which I'm pretty excited about, cascading active filters. And I have attempted to set up one second order filter cascaded with a second first order. That was the most awkward way to say that. The first filter is a second order filter, and the second filter is a first. You know what? Let's see the schematic. That was completely backwards. But that's how I set it up. So here's my filter. I have the voltage source, which is our audio input, going into a 10 kilo ohm resistor that has a feedback loop from a 100 nanofarad capacitor. That's our first low pass filter. And then we have a second low pass filter right here, another 10K 100 nanofarad capacitor. We have the first stage of our filter set up as a unity gain. So we just have V out back to the negative side of V in on my op amp. And then we have a second entire stage, which is a second low pass filter, RC. Again, 10K, 100 nanofarad. Over here, we have a gain stage to overcome any of the losses that may have happened and just, boost the signal. Who knows? Let's just see if that helps get our signal up out of the noise floor. And perhaps we can see more of that slope. We want to see a nice, steady slope. So I am going to, this is what I have wired up right now. You know what? Let me zoom in a little bit more so we can see a little bit better. So here are the components, 10K, 10K, 100 nanofarad, 100 nanofarad. Second stage, 10K, 10K, 33K, and 10K to set up my feedback loop, giving me a gain of about 3 according to my estimations. I want to simulate that. So I've set up a simulation that goes from 20 hertz to 20 kilohertz, which is the normal auditory range. And I'm going to hit play to run my simulation. And we will see if that simulation works. So according to my circuit simulator, I should have, let's see, about 10 dB of gain is good. It's going to give me a little bit of gain, or maybe 12 dB of gain, 12 dB of gain. And then if I go down here, my 3 dB point is about 93 hertz, which is good for a subwoofer. And it drops off at, let's see, if I go from 1 kilohertz to 10 kilohertz, let's see, how many dBs per decade? Let's see, 20, 40, almost 50 dB per decade. Almost. Does it match the measurement? That is the question. So that's my simulation. I'm going to go back to my webcam and let's talk about the measurement a little bit. So I have everything plugged in to my handy dandy oscilloscope. I am presumably the oscope wizard. That is how I've billed myself. I'm pretty good with oscilloscopes, honestly. So we're getting a measurement out of here. And what I have going into the oscilloscope right now is on channel 1, I have my input voltage. And then on channel 2, I have the output of that entire filter. So both stages, the first stage and the second stage. And I have kind of a rat's nest of wires here running through all the stuff to get to this TL72. TL072? TL072. But I've wired everything up in my schematic. So on channel 2, if we did an FFT of it, it should roughly match. It should roughly match our simulation here. I could probably make that bigger. There you go. Our simulation. Might even be able to get this out of the way. Oh my goodness. Now we can really see our simulation. I wish. No, it's already logged. It's already logged. I was looking at this waveform configuration. There's the downside of using Easy EDA is it doesn't have a ton of tools when it comes to the simulator. I would really love to be able to place a marker on this waveform. Apparently that used to be a thing, but it's a bug right now. And I can't get it to work. Be that as it may, let's take a look at just the oscilloscope, and I believe that is the button that allows me to do that. You know what? I can also move myself out of the way over here. So we can see the frequency response of my channel. So what I have here, as I said, channel 1 is the input voltage, channel 2 is the output voltage. And this math 4 is the FFT of channel 2. So this is the FFT of my output voltage showing me the filter response. And is it following roughly what I think it should? You know what I can do. You know what I can do. So first of all, I'm going to save this filter response really quickly so that I don't lose it. I'm going to have to remember how to do it. There we go. Reference waveform. I want to save math 4 as a reference waveform. That way, I can use it for comparison. So there we go. There's my reference waveform. If I was to hide these other waveforms, I don't really care about them right now. I'll even hide my reference waveform and let's make some measurements right here. So I can actually throw some cursors on this waveform. I would love to track the waveform. Can we track it? Let's move it up here. Let's see. So down here, I can see my measurement. So down here in the full passband, at the bottom, down at 100 hertz, I am at, whoop, wait a second, get all the way down there. All the way down there. Why are you not going all the way down there? There we go, all the way down there. 100 hertz, let's see, 8.4 dBm. So if I, wait a second, have I messed up my 100 hertz is where it's starting. Start frequency 100 hertz? No. 10 hertz, 10 hertz. I was like, wait a second. I feel like I'm missing some stuff. Whoa. You know what? I don't have enough time. Get some more time here. And let's make this go to min. There we go. 20 hertz. Perfect. Perfect, guys. Perfect. We're gonna let this run for a little while. So what I've done here is set up, as you can probably tell, something weird is happening with this FFT. And that is because I have made it a max hold. So that is what I actually am curious about. I'm gonna let it run for a little bit and just build up a nice flat waveform. As you can see, each run, it's getting a little bit lower. Because my passband should be about 10 dB, and that's the gain we set up roughly. And you can see, 10, 12, it's getting up there. It's getting up there. You know what? While it gets up there, I'm going to have some good and plenties, because it is Baby Friday, and we should enjoy ourselves a little bit. And somebody, when we were having a debate over toothpaste flavors, said chocolate, and then I mentioned licorice. Good and plenties are licorice. So I'm on the I enjoy that divisive flavor side of things. Can't help it. Love it. I want to go back and update my reference waveform. So let's update R1 with my new math. So now I've got R1 over here. I'm going to hide it. We're going to remember that because that is going to be what we use to compare. Okay, so we have what? 11.9 dBm. That looks good. And if we use marker 2 over here, and we look for -3 dB, wow, that was completely lucky. We are at 98 hertz, which, I mean, goodness gracious, is almost spot on for our simulation. And we can see that it does roll off pretty steeply. So if I go all the way out to 10 kilohertz, get not on one of these peaks. So I'm getting some weird harmonics through there. But I do have a delta of 33 dB, so I don't quite have that 50 dB of filtering through here. And most of that is because I'm kind of running into the noise floor of my probing and my signals. So this is a place where measurements really struggle against simulation when you have to deal with actual physical connection. But be that as it may, we're going to switch over. We've stored our waveform, and now I want to switch to using digital signal processing for this entire process instead of an analog filter. And maybe there's some kind of happy compromise between digital and analog. So I bring it back over and go back over to my monitor, we can see, what can we see? We can see, ta-da, I'm out of the way. We can see, sitting off, let's see if I get my webcam, we can see sitting off in the corner there, I have a Raspberry Pi. I love Raspberry Pis. I think they're so cool, and you can do so many different things with them. And one of the things that you can do with them is turn them into a squeeze audio device. which when I was researching how to synchronize wireless audio outputs, I thought about Bluetooth, but Bluetooth is just so laggy and its latency is kind of unpredictable. Squeeze box, and the thing I wanted to emulate was Sonos. Sonos has a beautiful wireless synchronization system. So when you have a Sonos system or a Sonos speaker by your television and you have another Sonos speaker in the back of the room, they all stay perfectly synced up, and they use network time protocol to do this, as far as I can tell. And Squeezebox does the same thing. So it is, weirdly enough, something from Logitech. So Logitech bought a company, and they have this Logitech media server, which you can put onto a computer, and then put this little Squeezebox, Squeeze Lite software on different devices. I'm using it on a Raspberry Pi, but apparently it will also run on a microcontroller, which I'm pretty excited about trying. And turn them into essentially little endpoints that all can be synchronized up. And that's what I'm running right now. So if we go over to my server, which I'll probably do another video on how to set all of this up because I think it's very cool. I've set up a couple of things on my Logitech media server, which is actually running on my DIY Sonos style amplifier. Tune in later to see how I set all of this up. But the point is, I can run some plugins that allows me to group different players together into different pods, or, well, different groups. Group them into groups, that is what it is doing. And I can have some members in that group. And so I have one for the techno layer, that's here, and then a group for the driveway, that's, out there. Eventually, everything will be in the driveway. There'll be two things: the main amplifier and then the wireless subwoofer. But for today's experiment, I have a group called the techno layer, and I have a Pi Core player. So I'm using the Pi Core player. Let's see. If I just go to Pi Core player, you can download it. The cool thing about it is it's based on Tiny Core Linux, so not Debian, which is what most of the Raspbian OSs, or Raspberry Pi OSs, are based on. And it is a tiny little, like, 40 megabyte file that you can flash onto here. A couple of major benefits: it boots up super quickly and can run on any of the Raspberry Pis flawlessly. I am running it on a Raspberry Pi 2. So it's I'm running it on a really old Raspberry Pi that doesn't have even Wi-Fi built into that old Raspberry Pi. And through the magic of this Logitech media server, I'm going to actually turn that old Raspberry Pi without Wi-Fi into an AirPlay endpoint that I'm going to be able to AirPlay stuff from my phone out to that Raspberry Pi, hopefully. And it is going to require a couple of tweaks. So what I want to do with this Raspberry, all that can be a deeper explanation later. Mostly, I want to use the DSP that is available in my audio port for the Raspberry Pi. So the DSP is an equalizer that I can now configure on the fly in the Raspberry Pi, and it can essentially do all those fancy equalization curves that I was building with resistors and capacitors and op amps, all inside of the silicon on the Raspberry Pi. So I need to do some changes to my board. First of all, since I'm using a Raspberry Pi that has a different ground than this floating ground, I don't want to shock myself. I'm going to unplug the signal, or the power from my board. So now this whole thing is turned off. And I am going to turn off the signal generator here really quickly, because I'm not going to actually use the signal generator from my oscilloscope. I'm going to use the Raspberry Pi as a signal generator. And I'm just going to look at the output of the Raspberry Pi. So on my phone, I have, let's see, I have a signal generator, a piece of software, which I can show you really quickly. Signal generator right here, and we're going to make a similar sweep to the one we were doing. We were just doing 20 hertz to 20 kilohertz, and we are going to essentially do the same thing. So let me set the stop frequency. Oh, 21 hertz, 21 kilohertz. We want to do 20 kilohertz. 21, 2, 3 kilohertz. Ooh, it can't focus on it. Too much. It's too much happening for my poor webcam. But I have it. You should be able to hear a little. It's very high pitched there at the end. But there you go. You heard that. So now I want to send it. Let's pause it. I want to send it to the techno layer. All right. Oh my gosh. Oh my gosh. Oh my gosh.
5 minutes remaining.
5 minutes, guys. 5 minutes. This is for real. Let's redo this. 1, 2, 3, 4, 5. Hit start. Back to my main scene. We have it hooked up. Let's bring out on my oscilloscope. So now we want to look at my oscilloscope really quickly. Do it. Whoa, whoa, we got some weird things happening. Oh, there we go. There we go. Got the oscilloscope. There we are. If I start this, what is channel 2 going to do? I hope that channel 2 is going to do some stuff. Channel 2. Yes. Yes. Let's turn the volume all the way up. Look at that. It's working. It's working. It's working. I might need to scale channel 2 a little bit. Now, I am using just the audio output from the Raspberry Pi, for better or worse. Generally, just the audio output of the Raspberry Pi itself is pretty bad, but we're just trying to compare some DSP. So I have this reference waveform, which is our analog filter, and how does that compare to just doing this DSP on my high-core player? So let's get out of that. Go back over here. So I have my adjustments. I might even be able to show both things at the same time. Okay, that's pretty cool. So if I take this, I'm showing this, doesn't quite fit on the screen, does it? I lost some of it. Okay. That's okay. That is okay. Uh-oh. No, hitting the wrong buttons. Want to get this working. Configure. I'm going to do a really hard cut for everything above 125 hertz. This is like an extreme example. Let's save it. And let's go back over here to my FFT and clear it. Clear it. It's working. See, it is rolling off now. We are getting a roll off. Are we clipping it all? It is not. Let's see. It is rolling off, right? We've made our own little roll off, but hey man, not quite as good. Not quite as good as it was. Potentially not. Now, one thing to note is I can let me adjust this probe a little bit. So I have a attenuator on this probe that I probably don't need right now, because I'm looking at a smaller signal. So if I go into my probe setup, turn off the attenuator, plug it in. Let's see what it looks like. Now, I might be overdriving the probe. No, look at this. Even though I have my filtering set up, here, I'm going to make an even harder core filter right here. Let's go over and what if I just held 1,000 waveforms? Am I still doing the max hold? Max hold. I don't know, man. It's doing it. It is filtering it. You know what? I wonder if it's because my volume is like maxing out. Let's turn the volume down a little bit so I'm not overdriving. So I've turned the volume down on my signal generator over here. Let's see what that filter shape looks like. Oh, here we go. We're getting a better view of what the filter actually does instead of overdriving the volume. That's one of the challenges I'm going to have is how to prevent it from overdriving. But if we put reference 1 on the same plane as our DSP, it looks like analog filtering. It looks like the analog filtering is keeping up. I would say. I'm pretty impressed with that. So now I was a little bit kind of on the analog filter, but now I'm looking at it. There might be a place for an analog filter. And what I think ultimately I'm going to do is use the DSP running through just a simple passive RC filter network. So just a resistor and a capacitor. And that way, I have the best of both worlds. I can control it. The RC will set up a fundamental subwoofer filter, and then I can use the DSP to tweak it a little bit, which might be kind of cool and give me the best of both worlds. So the really cool thing about DSP is that took a lot of components on a breadboard or on a printed circuit board or in a device, and all of that can be replaced with an algorithm running inside of a piece of silicon on a processor. That is the magic of DSP. It's magical. It does all kinds of cool things. Anyway, thank you so much for hanging out in the Techno Lair for about a half an hour on a wonderful baby Friday. I don't know all the nerds in the world, and I would love to meet them, so please share this with a nerd in your life. We're going to get back to this wireless sub in a couple of weeks because I'm waiting on some microcontrollers. I want to make, instead of using a Raspberry Pi for this project, I really want to use a microcontroller. I think it would be really neat. Hopefully it would boot up faster. That's one of the things I want to compare, like how fast does the microcontroller boot up this little tiny Pi Core player versus, or the Squeeze Lite implementation versus how fast does a Raspberry Pi boot up. So microcontroller versus Raspberry Pi showdown, which one is faster for a wireless subwoofer, which is kind of a weird application, but hey man, you came here. We're going to nerd out. We're going to do nerdy things. I'll hang out in the chat and see you guys later. Bye.